Black holes. So what we're going to do today is we're going to analyze the motion of a star. The star has a mass, a velocity, and it bends around an elliptical path. So we need to figure out what that means for the net force on the star. We're going to need some fundamental principle, which is Newton's second law, which is force equals mass times acceleration, or you can use the momentum equals, or the change in momentum equals F net times the change in time. So my prediction is that the mass of the invisible object is going to be much more massive than the mass of the star. The mass of the object must be larger than the mass of a star because the star's motion is revolving around that object. In this case, we are going to assume that the only net force acting on the object is the gravitational force. So that must mean that the motion of the star is totally due to that gravitational force and its initial acceleration. So the star is trapped in the gravity of the object with a perpendicular change in momentum, and that's governed by the speed, and a perpendicular change governed by the direction of the momentum change. So we're going to need Newton's law of universal gravitation to figure out the net force on the star, and from that, the mass of the object. And that gravitation equation is the gravitational constant times both masses divided by the radius or the distance between the objects squared, where m is the mass of the star. Again, uppercase M is the mass of the black hole, and r is the distance between them, and g is the gravitation constant. We are going to assume that the invisible object is the black hole in this case. So for the calculations, we're going to use the star data as given to us, along with the mass of the star and time step of the motion to determine the net force on the star from the black hole. We're going to calculate both the parallel and perpendicular components of the force acting on the object. From this, we can observe with more clarity how the net force vector is formed from the combination of these two vectors. We know that the gravitational force is the net force. So we get the position data from the star data, which we can use to calculate the initial and final velocity vectors. We're going to use these to calculate the change in momentum. We're going to do this iteratively, so many times, and that's going to give us the net force in all locations. The net force at the end is the most important to us. We're going to put all this into VPython and we're going to code this. So I have position data here. This is the path that the star goes around. So my conclusion is the mass of the black hole was found by rearranging the gravitation equation to solve for the mass of the black hole. So I ended up getting 3.565 e to the 31st kilograms, which was correct. So my prediction was correct. The black hole was much more massive than the star, and the force on the star by the black hole affected the motion of the star. So we have two questions. So if another black hole was replaced, this one, but the motion stayed the same, we would know that the mass of the black holes are close to identical. If the motion of the star was affected, you know that the new black hole must have a different mass. Another question is about the net force change. If the net force changes, the motion of the object changes, since F net equals change in momentum divided by the change in time. The net force and the change in momentum are identical, but a change in the net force causes a change in momentum, which is not necessarily true the other way around. Therefore, the F net parallel, perpendicular, and the total F net are equal to the change in momentum parallel, the change in momentum perpendicular, and the total change in momentum. So this is lab number 3, which is black holes.